In this presentation, we're going to cover the very basic technical concepts behind the ISA100.11a standard. We're going to show how user requirements fit with the system architecture, and this will be at a very basic level, as an introduction for people who know very little about the standard. For those of you who are familiar with the standard, we hope this will help you to explain it to your colleagues. We will put this webinar on the web for reference and training purposes. So this webinar is pretty basic. For future tutorial webinars in this series, we're going to build on this base, getting more specialized and going into more detail. At the end of the presentation, there will be time for you to ask questions. Okay, the screen works, that's good. In this short webinar, we will cover the high-level user requirements behind ISA100.11a, its system architecture, and how these requirements and the architecture fit together. First, we will cover high-level requirements. The standard was designed to meet all of these requirements at the same time. Then, we're going to discuss technology in the standard that addresses these requirements. The standard is intended for a broad range of applications, not just monitoring. The standard is built on the base of IP, the Internet Protocol. This fundamental decision enabled ISA100 to integrate seamlessly with the latest networking technology and continue to do so into the future. The standard incorporates state-of-the-art wireless mesh networking designed to complement and extend IP standards. And the standard has a fully specified and control-ready application layer. It is flexible to integrate with a wide variety of systems. This presentation assumes some very basic familiarity with the ISA100 standard and its marketplace. The basic goals for the standard are summarized on this slide. ISA100.11a is a wireless standard for sensor devices. It is intended to untether a broad range of field bus type applications. Generally, this tutorial series will assume basic familiarity with field bus applications and products, and we will focus on wireless aspects that might not be so familiar in the wireless world. There have been several efforts to formalize user requirements for wireless systems. For this presentation, I selected one of the early results. The ISA100 standard originated from a project with the United States Department of Energy. The requirements listed on this slide came from that project based on extensive interviews with users. These requirements are fairly high level, but for an introductory presentation, they seem to be about right. Anyway, this diagram indicates that ISA100 was designed to meet 11 key user requirements, all at the same time. First, a wireless system must provide state-of-the-art security. Second, it must provide reliable wireless communication. Third, it must provide deterministic power management of battery-powered sensors. Fourth, it must be open, allowing users to select the best products for a given application. Fifth, it must support multi-speed monitoring. Some devices might report every quarter second, while other devices might report every few minutes, all on the same network. Sixth, it must be multifunctional, supporting a range of applications with one system and at the same time. Seventh, it must be scalable to tens of thousands of devices in a single network. Eighth, it must account for global wireless regulations so that one instrument can be deployed anywhere in the world. Ninth, it must provide predictable quality of service that can be configured by the user to meet particular application requirements. 10th, it must be multi-protocol at the application layer, compatible with the user's choice of host system. Finally, completing the circle and wrapping all of this together, you get a standardized interoperable platform that is control ready. We could have a full day seminar on any one of these objectives, and it's covered by ISA100. Today we have limited time, so we're just going to cover the highlights. Now this slide provides a short description of each requirement from the previous slide. All of these requirements need to be supported by the same network at the same time. When these requirements are involved, users don't give partial credit. First, security. The cryptographic building blocks in ISA100 are well proven. Users were very involved in the ISA100 design, and they were particularly interested in security. Users provided excellent guidance to the ISA100 committee, and this guidance is reflected in the standard. Second, reliable communication. The network needs to provide 24/7 operation without outages. When a message is sent, it needs to arrive at the other side of the wireless link. It also needs to arrive quickly enough to be relevant. And when the message arrives, the user needs strong security assurances that the data is valid. Third, good power management is essential. When a device is designed for a certain battery life, the network needs to respect that device's battery limitations so that the device actually operates for its entire lifespan as designed. Fourth, the standard must be open. Of course, that is what standards are for, but users want to be able to buy instruments from multiple vendors. Fifth, real-world systems are multi-speed. Some devices might report data every 30 seconds. Others might report data every second. But a single network must support all these different data reporting rates at the same time. Do users install a different Wi-Fi network for each type of Wi-Fi device? Of course they don't. A single network needs to be able to support any mixture of reporting rates, whatever the user needs. Sixth, following the same line of logic, the systems must be multifunctional. A single network needs to support multiple functions from monitoring to control. Seventh, the systems must be scalable. But what exactly does scalability mean for a wireless sensor network? Three aspects of scalability are noted in the slide. One aspect of scalability is that the network must be scalable in numbers. There can be 20,000 motors in a plant that need to be monitored and 20,000 valves that might be in the wrong position. This needs to be managed coherently, not as dozens or hundreds of little networks. Another aspect of scalability is that the network must be scalable in space. Monitoring applications, for example, motor monitoring, can be plant-wide in scale. These sensors will be installed in areas measured in tens, hundreds, or thousands of acres. Users need to see and manage this as one business network, not as dozens or hundreds of little home networks. Another aspect of scalability is that the network must be scalable in rates. Some devices might report every 10 minutes, and others might report every quarter second. Those devices might have totally different quality of service requirements, but they still need to operate on one network at the same time. The system needs to deliver that performance reliably and transparently. Moving on, point 9 is global usability. Global customers want products that can be deployed anywhere in the world. They don't want to manage different products in different regions. Suppliers also want one product line that can be sold everywhere. Ninth, controlled quality of service is essential. Messages need to be delivered reliably and on time. The network must provide exactly the quality of service required by each individual application. 10th, multi-protocol is a functional user requirement that we hear over and over again. Users often want their wireless devices to fit seamlessly within their wired application framework. This all results in a network that is control-ready. Users are looking for interoperable products that solve real problems right away, ranging from monitoring to control. This slide shows more of a summary view of user requirements. Users want the standard to result in systems that are reliable, scalable, open, secure, multifunctional, and easily deployed. These very general user requirements can be mapped into more detailed technical requirements. For this presentation, we will zero in on three essential areas. First, ISA100 covers a broad range of applications worldwide, not just monitoring, and not just small networks of very expensive devices. Second, the standard includes a state-of-the-art wireless mesh fully integrated with standard IP. ISA100 leverages mature IP technology for scaled solutions. Third, we will discuss ISA100's powerful, flexible, and extensible application layer. Users need legacy compatibility looking forward, and users also need a modern and extensible system architecture looking forward. The standard must allow users to select and evolve their own application frameworks to meet their specific needs. The next section of this presentation describes the classes of applications targeted by ISA100. This picture shows a user who needs to do many things at the same time. This diagram shows a very simple but important configuration. Two devices are within very close proximity of each other. One device publishes data to the other device at quarter-second intervals. This is not what most people would call a monitoring configuration, but it is a fundamental requirement for the network. How do we think about a system that supports this and other important configurations? The next few slides will look at the application class framework used by the authors of ISA100 to make network architecture decisions. ISA100 was designed to cover a wide range of applications, summarized in the standard as application classes 0 through 5. Monitoring applications, called classes 4 and 5, are shown at the bottom of the chart. Control applications, classes 1, 2, and 3, are shown in the middle. Safety, class 0, is shown at the top. The arrows to the right show the nature of the applications. Generally, when the user class is more critical, performance requirements will increase. The single device being used for a Class 1 application will typically need more network resources and performance than another device used for Class 5 applications. This is indicated by the arrow labeled more performance. It is also anticipated that there will be more devices used for monitoring than for control, potentially tens of thousands of devices in a plant. This is indicated by the arrow labeled more devices. This slide duplicates some usage class examples from the standard. We don't have time today to discuss these examples in any detail. It is provided here as a convenience, so you can review it yourself. A quick scan of this list will show that ISA100 is designed to support a broad range of applications. A single wireless architecture is intended to support high-frequency cascades and history collections all at the same time. So, the standard isn't just for monitoring. In 2006, at the start of ISA100, the committee considered designing two standards, one for monitoring and another for control. But when we reviewed actual technical proposals, we saw that the users and suppliers wanted one standard that would handle monitoring extremely well and also handle a reasonable cross-section of control and even some safety applications. Why is this? Some demanding Class 0 through 3 applications will always need a wire. Some applications might require more advanced radios that don't even exist yet. But a reasonable cross-section of applications can be wireless using a commodity radio. For these applications, people want one system that can handle most of their wireless sensing needs. ISA100 recognizes that a commercial-grade radio in the standard might not be suitable for some safety and control applications. But for applications where that radio is appropriate, we were careful to allow for such use. So, the ISA100 architecture supports a mix of classes 1 through 5 and optionally class 0. The standard needs to support all usage classes at the same time in any reasonable combination that the user desires. The next two slides summarize the presentation so far. ISA100.11a is designed to support a broad range of applications with one network and all at the same time. This network is multi-speed and multifunctional. Most end users have asked for a coherent, standards-based wireless solution that supports instruments used for a bunch of different things. Manual or automated monitoring, where there is not need for timely data or alarming. Automated monitoring, where timely data and or alarming reporting is essential. Automated control, and occasionally safety, because many sites have a combination of these. Typically, it is expected that the number of devices will be higher for monitoring, but ISA100 needs to accommodate all usage classes at the same time. ISA100 is scalable, supporting high numbers of devices with potentially many thousands of monitoring points per site. ISA100 is scalable to support high performance in a subset of devices. Specifically, the standard anticipates devices that need to report at rates of 1 per second or faster with a high quality of service. ISA100 needs to allow for low-cost devices with small batteries. Not only does the network need to support thousands of devices, those devices also need to be economically reasonable. Networks need to be manageable, particularly as they scale. And it needs to be all one network from a user's point of view. The network needs to perform all functions at the same time at scale. And this is a nice segue to the IP part of this presentation, which starts on the next slide. These flexibility and scalability requirements naturally suggest that ISA100 build its future around the IP architecture. IP is, of course, a scalable, flexible, and well-supported communications architecture. We don't need to reinvent that. We can just build on it. Now let's discuss communications architecture. These pictures illustrate the idea that ISA100 is designed to cover a wide range of wireless communication scenarios and also allow for improvements to communication technology. This diagram shows how ISA100 maps into the standard OSI stack used by IP. The middle layers 3 and 4, are standard UDP and IP. Layer 3 in ISA100 is IP. Layer 4 in ISA100 is UDP. That is the scalability strategy of the standard. ISA100 is as scalable as IP because it is based on IP. Connected to the IP layer, in layer 2, is an ISA100 mesh. The important concept is that the ISA100 mesh is just below IP on the communication stack and fully compatible with IP. ISA100 has a special session layer optimized for communication to and from field devices. It provides end-to-end security and some diagnostic services. At the top of the OSI stack in layer 7 is an application layer. The application layer has an object model that maps cleanly into a function block approach similar to Foundation Field Bus. Presentation layer functions are covered by the standard set of services called application sublayer in ISA100. In summary, when we say that ISA100 uses IP, that means that it uses network and transport as standardized by the Internet Engineering Task Force, or IETF. The special wireless mesh capability, optimized for field device operations, is added below IP in layer 2. Above UDP in layer 5 is the session layer. Application services are in layer 7, also above UDP. ISA100 is literally an extension of IP. We don't have time today for a careful review of ISA100 security, but we can at least cover the basic security model and how it fits with the IP stack. The standard adds security protection below IP and above UDP. This wraps high integrity and optional encryption around the IP standard. As shown in the diagram, ISA100 adds security below IP at layer 2 and above UDP at layer 5. Transport layer security provides end-to-end protection of your data. As an analogy, end-to-end security protects your credit card data when you purchase something on the Internet. Transport layer security in ISA100 performs approximately the same function. It protects your data end-to-end. Data link layer security protects the lower level radio communication and fills approximately the same function as WPA in a Wi-Fi network. The result is that when data is received on an ISA100 network, the user has strong security assurances that the data is authentic. In addition, data can also be encrypted if the user requires secrecy in addition to authentication. Now, let's see how the IP approach in ISA100 impacts the user experience in actual practice. This diagram shows a scaled network configuration. The ISA100 radio cloud is shown as a single mesh with multiple IP backbone connections. In this configuration, the gateway is shown as an Internet appliance without a radio. ISA100.11a messages flow over the backbone network. Now let's compare that to a mesh-centered design. I call this mesh-centered because the design starts with the radio mesh and then connects stuff to it. Since backbone communication is unspecified, it is shown as a series of question marks, one for each gateway. The backbone might be IP, or it might be anything. The diagram shows several radio meshes, all running at the same time, but not connected or coordinated with each other. Each mesh is attached to a device called a gateway. The diagram shows that each gateway device also hosts a management function. In this configuration, each gateway has a radio, and no backbone is involved in each little wireless network. Each network stops at the gateway. At the gateway, the data is translated into something completely different, such as Modbus or OPC. The connections on the other side of the gateway are shown as a series of question marks, suggesting that the high-side interface isn't specified by the standard and could be just about anything. Now, let's compare that to the ISA100 approach, based on IP. The happy face on the left indicates the end-user experience as this installation scales. From a practical perspective, the backbone connection device is intrinsically less expensive and easier to manage when it is just a backbone connection and not also a gateway. The relatively low cost and easy support of a backbone device makes it practical to install more of them. The computer science is pretty simple. More backbone connections will result in a stronger mesh when compared to an equivalent network with fewer backbone connections. There is another computer science advantage that's not so obvious. The scaled mesh with many backbone connections generally operates more efficiently and reliably than several discrete mesh clusters. A single scaled mesh has fewer edges and therefore has fewer edge conditions. In these kinds of radio systems, the edge conditions are deadly, and it's better to design them out of the network at the architecture level. So here's the mesh-centered design again. The network is scaled by duplicating lots of little meshes. And now here they are shown together. Now, both of these views are supported by ISA100, but the designers of the standard intended that scaled installations will look like the network at the top of the slide. Small systems or evaluation systems will tend to look like the installations at the bottom of the slide. But as the systems scale, it's expected that users will prefer to leverage the IP backbone as shown at the top of the slide. So, to summarize the IP part of this presentation, let's review the advantages of a mesh that is designed as an extension of an IP backbone. The ISA100 network architecture allows for multiple clusters of devices that appear as one network, even if they are spread across the plant. Each subnet can be quite large, up to 30,000 devices, and there is no limit to the number of subnets on an ISA100 network. The entire plant can be managed as a single network if that is what the user wants, regardless of the number of devices involved. Since the entire plant can be configured as a single ISA100 network, management of a wireless sensor network can be centralized in a plant. This results in simplified management, coordinated use of the radio channel in the plant, and the ability to share backbone resources such as gateways across the plant. Now, let's move to the next section of this presentation. So far, we've hardly mentioned that the ISA100 network involves radios. Of course, the standard needs to provide state-of-the-art wireless capabilities, and now we'll discuss that for a little while. The wireless philosophy is simple. There are many trade-offs in the design of a wireless system. Most wireless system standards make these trade-offs inside of the standard. If the solution designer wants to make a different trade-off, that's not allowed. ISA100 is unique in this regard. The authors of the standard recognize that there are trade-offs and that different choices are reasonable in different situations. Therefore, the standard is flexible. The trade-offs are left to the solution designer, and the device can be configured in different ways to achieve different system-level results. Future webinars will explore some of these trade-offs in more detail. Today, as an introduction, we will try to give you a general sense of how we achieve this flexible result. For radio communication, this standard uses the IEEE 802.15.4 direct sequence radio at 2.4 gigahertz. This is the same radio used by various other standards. It was selected because it is available from multiple sources, is backed by IEEE, and can be configured to work well worldwide under a wide range of local radio regulations. The IEEE radio includes 16 channels, numbered 11 through 26, as shown in the diagram. If you want to review more exact technical information, a technical reference, a section reference from the standard is provided at the bottom of this slide. You will find references like this on several slides that follow. So here's another picture from the standard. IEEE originally designed 802.15.4 as a very simple radio that operates on a single radio frequency. In practice, people have found that problems resulted from reliance on a single radio channel, partly because the radio is so simple. Therefore, channel hopping was added to ISA100 to make the radio work more reliably. This diagram shows one of the channel hopping patterns built into the standard. Time is shown across the bottom and radio frequency along the side. Each arrow shows a hop to another channel. Note that each hop changes the center frequency by at least 20 megahertz. Research and experience has shown that there is a very high probability of success using this approach. With channel hopping, each link becomes stronger. In practice, channel hopping results in a much stronger mesh network. So, having established that channel hopping is useful, what's the best way to channel hop? ISA100 supports two styles of channel hopping, called slotted hopping and slow hopping, in the standard. In slotted hopping, each transmission is in a different time slot, and each time slot is on a different frequency. That is shown as very short gray dots in the top diagram. Slotted hopping is similar to Bluetooth. Like Bluetooth, slotted hopping requires that nodes maintain really good time synchronization. In slow hopping, the radios spend more time on a radio channel before switching to another channel. This is shown in the middle diagram. A device doesn't need such tight time synchronization in slow hopping. For example, slow hopping can be very useful for devices that are searching for a network. Slow hopping can also be useful for devices with small batteries that have been asleep for a long time. The bottom of the slide shows a hybrid configuration, with some time periods using slow hopping and other time periods using slotted hopping. ISA100 supports slotted hopping, slow hopping, or any combination that the system designer selects. To my knowledge, actual systems are all hybrids to some degree. Now, let's look at the network itself. This diagram is copied from the standard. It shows a wireless mesh network on the left, a backbone network in the middle, and a plant network on the right. In this configuration, there are two types of ISA100 infrastructure devices. Backbone routers provide an interface between ISA100, wireless mesh, and the backbone. On the backbone, we show two gateway devices, both labeled GMS. That means that the devices combine the gateway, system manager, and security manager roles. In this particular configuration, one gateway is active and the other is a backup. Now let's look at some routing examples. We will start with a simple example where data flows from a field device through 4 wireless hops to a wireless gateway. The 4 hops are labeled 1, 2, 3, and 4 in the diagram. As you can see on this slide, if there is a problem with the preferred route, a backup route is immediately used instead. Now let's add a backbone to the picture. The message flows through a backbone router to an infrastructure device that combines gateway and management roles. In this case, the gateway doesn't have a radio. The gateway just uses wired IP communication. The standard leaves these decisions to product designers. This slide shows peer-to-peer routing. Peer-to-peer communication is fully supported by ISA100.11a in a coherent way through all layers of the stack. This slide shows peer-to-peer routing over a backbone. It illustrates the principle that any ISA100 device can communicate directly with any other ISA100 device as long as it has the security credentials, just like IP. The last few slides have covered a lot of material very quickly. What are the main points to remember? Here are a few. ISA100.11a is based on IP. This provides a proven base and a flexible roadmap forward. The standard is secure, based on meticulous application of well-proven cryptographic techniques. The standard is scalable, as scalable as IP itself. The standard includes configurable and flexible mesh network. Solution designers can make their own trade-offs to give users exactly the performance that they need. Networks are reliable and energy efficient at the same time. Networks are modular. Devices can be built to perform any combination of functions that your users need. Networks are open. There is no secret sauce, and the key communication interfaces are fully defined. So far, we've been talking about networking, but once the network is operating, the user should not even notice that. when the network is running, what can you actually do with it? This brings us to OSI Layer 7, the application layer. As we discussed earlier, ISA100 is designed to support multiple protocols. This diagram shows that a single network can carry data from multiple application protocols at the same time, much as the Internet can carry data from many different types of applications. Some examples are shown. Native mode is intended as the primary way to report data in ISA100. The object model in the standard provides a fully specified way to report data. We will describe native mode on the next slides. FF, or Foundation Field Bus, is shown as another alternative. The object model in ISA100 was specifically intended to integrate into the object model of Foundation Field Bus. For example, a unit code of 1001 in ISA100 means degrees Celsius, and it's also the coding for Foundation Field Bus. ISA100 is designed to be extensible, so that for a host, a wired Foundation Field Bus device looks pretty similar to a wireless ISA100 device. HART is shown as another alternative. Mapping ISA100 to HART is less natural than FF because HART uses a command response model while ISA100 uses an object data model. Still, integration with HART application layer was anticipated to a tunnel object that tunnels commands from any protocol. In each case, the diagram shows data from different types of devices being forwarded to different hosts. The standard allows users to select the best application model for the job. This is a natural consequence of following the OSI layering from the IP world. The designers of ISA100 were careful to preserve that flexibility at the application layer. As a simple example of the capabilities of the ISA100 native application layer, let's take a quick look at data publication. The device shown in this example has three sensors: a temperature sensor, a pressure sensor, and a binary contact sensor. Each sensor has an object with the ISA100 application layer. The application layer also has a concentrator object, which is also fully specified by the standard. The host, through the gateway, receives these three readings periodically, such as every 10 seconds. This is all accomplished by configuring a standard ISA100 concentrator object in the device. This is just one example of the capabilities of the native ISA100 application layer. So, the ISA100 application model meets the user's requirements for flexibility and extensibility. Native mode supports function blocks that cover many basic use cases. For input blocks, the standard supports analog and binary inputs using the same engineering units as Foundation Field Bus. Data from input blocks can be published through concentrator objects, as shown on the previous slide, or the processed data can be read directly. Furthermore, the standard includes an alert model so you can configure the device to report exceptions when thresholds are exceeded. Output blocks are essentially the mirror image of input blocks. An application can be configured to subscribe to data directly from another device on the network without involving the gateway. The native application layer also supports bulk transfer. Bulk transfer can be used to upgrade the firmware on a device. Alternatively, bulk transfer might be used to transmit waveforms such as vibration data from a device to the host. This is all specified by the standard. ISA100 native mode provides baseline functions that can be extended. The ISA100 Wireless Compliance Institute, which is us, is building specifications that extend the base capabilities of ISA100. We have already written and validated profiles for temperature and pressure. We have already written and validated extensible device descriptors and capability files, leveraging pre-existing standards and tools from the wired world. We have carefully chosen schema that can be represented in ISA 104 and also in XML. We will cover that in a future webinar. As noted on the slide, tunneling is also defined by the standard. This enables legacy non-field bus commands and services to be transmitted over the ISA 100 network. Tunneling is already being used to tunnel hard commands over the ISA 100 wireless network. The same approach can be used for other protocols, such as Modbus, Foundation Field Bus, Profibus, 1451, and so forth, all on one network, all leveraging IP technology. So, the ISA 100 application layer is designed to facilitate the creation of control-ready devices that are fully interoperable. The object-oriented native application layer is derived from Foundation Field Bus, HART, and Profibus. It is lightweight, extensible, and powerful, suitable for wireless monitoring and control. Devices report value plus status, similar to Foundation Field Bus, HART, and Profibus. Baseline features that are shared among the various platforms can be mapped with the gateway. Special features and extensions can be tunneled. Jitter and loop times is controlled. The application layer creates contracts with the network to support its requirements for scheduled, latency-controlled, phased periodic messaging. Peer-to-peer communication is fully supported, either in publish-subscribe mode or client-server mode. This is integrated to all layers of the stack, leveraging IP. Now, let's get back to those original user requirements in the start of this presentation. First, ISA 100.11a provides state-of-the-art security. Second, it provides reliable wireless communication. Third, it provides deterministic power management of battery-powered sensors. Fourth, it is open, allowing users to select the best products for a given application. Fifth, it supports multi-speed monitoring. Some devices might report every quarter second, while others might report every few minutes, all on the same network. Sixth, it is multifunctional, supporting a range of applications with one system and at the same time. Seventh, it is scalable seamlessly to tens of thousands of devices in a single plant. Eighth, it accounts for global wireless regulations so that one instrument can be deployed anywhere in the world. Ninth, it provides predictable quality of service that can be configured by the user to meet particular application requirements. 10th, it is multi-protocol at the application layer, compatible with the user's choice of host system. Finally, wrapping all this together, you get a standard that is flexible for delivering innovative solutions. So, in this short presentation, we have tried to show how we meet each of these core technical requirements. The key takeaways are, first, that ISA 100.11a provides a secure, reliable, and scalable platform. This is accomplished by extending standard IP with state-of-the-art wireless mesh. Second, that the application layer is flexible and extendable, adaptable to a wide variety of usage scenarios.